Thanks a lot, Ben. Yeah, so now what I would like to do for this second part of my mini series of talks here is to talk about examples of Lagrangian mean curvature flow. And I want to be as explicit as possible. So I'm going to start just with Lagrangian graphs. Just think about the graphical case. So we just let f be a function from Rn to R and consider L to be graph of the gradient of f. So remember what I meant was the set of x plus I grad f of x, which the x is in Rn. MECM. We know this is Lagrangian, and now what I want to try to compute is what is its Lagrangian angle, is it exact or not, all that kind of stuff. So let's start off with the Lagrangian angle. What is it? So you can calculate it, and what you'll discover is that it's the following formula, so don't be scared, it's not that bad. So it's the sum, j equals 1 up to n, of the arctangent of lambda j, where lambda 1 up to lambda n are the eigenvalues of the Hessian of f. Okay. So it's the sum of the arctans of the eigenvalues of the Hessian of f. Okay. That's what it is. So in particular, this is a nice single-valued function, so it's 0 Maslov. So it implies 0 Maslov. Now let's take that D'Urville form and restrict it to L. And what you'll discover is that it's d of something. It's d of x rad f minus 2f. So again, I would definitely suggest that you do the exercise and show that this is true. So that means that L is exact. Particular. And now I can tell you what Lagrangian mean curvature flow is for graphs. It's just I varied the graph functions little f by theta, which is just this sum of the arctans of the eigenvalues. Okay. That's the equation that you need to solve. Right? So this is a fully nonlinear but parabolic partial differential equation. Okay. So that's what you're up against. All right. So let's have a look at a special case, which is to think about dimension 2. Let's take n equals 2. And I want to define the Lagrangian catenoid. So we heard about catenoids in the previous talk, and I'm sure we've heard about catenoids a lot during the week. Now what you discover for n equals 2 is that this equation is particularly nice. So you see that if I do, well, this one, you know, this is just elementary trigonometry. If I do the arctan of lambda 1 plus the arctan of lambda 2, then that's the arctan of something. It's the arctan of the Laplacian of f over 1 minus the determinant of the Hessian of f. Okay. So you can check that. And so you can see that if I choose my f to be harmonic, then it's going to be minimal, right? Because theta is going to be 0. So therefore, delta f equals 0 will imply that theta equals 0. So I'm going to let f be a half log x1 squared plus x2 squared, which is of course not defined on all of R2, but it's defined on R2 minus the origin. And then L, which is the graph of the gradient of f, is the Lagrangian catenoid. So it's, of course, it's R2 minus the origin. You can think of that as S1 cross R, so you can think of it, again, as a hyperboloid, as you normally do for a catenoid. And one thing you know about the usual catenoid is that it has planar ends. Right? So does this have planar ends? Well, let's just write it down. Let's just be explicit. What is it? It's going to be x1 plus I x1 over x1 squared plus x2 squared, and x2 plus I x2 over x1 squared plus x2 squared, such that x1 and x2 is in R2 minus 0. And so what I can do is I can send, so asymptotically, L looks like, well, if I make x1 and x2 both very large, then this term goes to 0, this term goes to 0. So it's just the real R2. Right? It's just the real R2. So this looks like R2 inside C2. And if I make x1 and x2 very, very small, then these go to 0, but these are going to infinity, right? So it looks like the purely imaginary R2. So it looks like the union of two planes, R2 union I, R2. Okay. So it's an exact special Lagrangian. So then here, of course, this is a harmonic function. This is special Lagrangian, and it's exact. Exact special Lagrangian, which has that asymptotic behavior. And that's called the Lagrangian catenoid. All right, now we actually have a more general construction. Any questions about this? Questions? Okay, so now we actually have a more general construction.
I have online request.
Yeah, go for it.
Can I ask? Can I request something? So just build the online box and not a light. Like if you can write a little bit.
What the limit looks like, or like, how do I take the limit?
No. So I'm just asking about the writing on the board.
Oh, yeah. Make it a bit bigger.
Not there. When you write when you write the next line on the when you write the next can anyway continue, please. Sorry.
Yeah. So
I'm saying that on the top line, you write on top of the board. The light falls, yeah, and then
oh, I see. Don't write near the top of the board. There's too much glare. That's what you're saying. Okay, I won't then. Okay, so right, yeah. So let me then. Oh yeah, right. So what I wanted to say is that I'm going to take. I have a more general construction, which are called Law-Lennecks. So if I take P1 to be the real Rn inside Cn,
thanks a
and I
lot.
take P2, is that better?
Yes.
Ah, good. And if I take P2 to be this, x1 to xn is in Rn, and I'm taking my theta 1 up to theta n all to be in 0 up to pi, and such that the sum of the thetas is pi. So suppose that I do that. I take a pair of planes. These are both Lagrangian planes, okay? And I impose this condition on the angles. Right? The sum of the angles is pi. Right? If I do that, so in this case, what would the angles be? The angles here would both be pi by 2. That's what this would say. Theta 1 would be pi by 2, theta 2 would be pi by 2. That's the example here. Okay. Whenever this happens, it was proved by Lawler. So then Lawler showed there exists an exact special Lagrangian with theta equals 0, asymptotic to the union of these two planes. And this special Lagrangian, L, and this special Lagrangian is topologically Sn minus 1 times R. So it's exactly the same topology as we had before, but just extended to higher dimensions. Okay? And if theta 1, if you're in the very special case that all the thetas are equal and equal to pi over n, this is called the Lagrangian catenoid in Cn, which is going to be SON invariant. Okay. All right. So these are very important objects in the study of Lagrangian mean curvature flow because they're asymptotic to a pair of special Lagrangian planes.
Hey, a quick question from
Yep.
Yeah. Hey, it's Rob. A long time no see.
Hey, Rob.
So in the n equals 2 case, you have the lowest order growth. It's like it's one lower than the green function. It's not log. It's 1 over. In the n case, what are the Lawler? How quickly do they approach those planes?
It's exactly the same. It's exactly the same. So it's the graph looks like the Green's function again, and you take the derivative. So it's one less than the
one
less
one less
than the Green's function. Yeah.
Yep.
Exactly. Yeah. Thanks, Rob. Yeah. Okay. So now I want to. So these are very important, but now I want to do a different example, which is the case of shrinkers, and I want to talk about the Clifford torus. So now my L is going to be the following. So it's going to be set of, so I'm going to scale this so that it has the right size. I'm going to take e to the I theta 1 and e to the I theta 2 and multiply by the square root of 2. So theta 1 and theta 2, just any real numbers. And that's going to give me a torus contained in C2. This is Lagrangian. And what you can check is that if you do omega restricted to L, then what you get is minus e to the I theta 1 plus theta 2 times the volume form on L. So it's a very easy exercise. I suggest that you do it. And so what that tells you is that the Lagrangian angle, as we saw, this is a bit like the circle case, right? In the case of the circle, it was theta plus pi by 2, right? It was the angle plus pi by 2. Here, the Lagrangian angle is theta 1 plus theta 2 plus pi. So that means that it's not zero Maslov, so not zero Maslov, as we knew it could not be. But you can see that h is going to be minus x perp over 2. And indeed, you see.
Please write a little below.
Oh, yeah. Sorry. And indeed, we see that the class of d theta is just 2 times the class of lambda. Actually, it is just 2. Don't even need classes. D theta is 2 times lambda restricted to L. 1/2. So you get indeed the monotone condition as you expected that you would get. Yeah. So it implies monotone, as we knew it had to be. So this is easy to calculate. All right, so that all fits with our theory, right? We said we couldn't have 0 Maslov self-shrinkers, and we said that they had to be monotone, so this is all as we expected. Okay, so I said that you couldn't have self-shrinking spheres. But there are some very nice Lagrangian spheres. So it's an interesting question to ask, what do they do under the Lagrangian mean curvature flow? So this is a self-shrinker. Okay, so there's a very nice Lagrangian sphere called the Whitney sphere. So the way that I'm going to write this down is as follows. It's going to be L. It's going to be the set of U1 plus I, U1, U3, U2 plus I, U2, U3, all over 1 plus U3 squared, where U1 squared plus U2 squared plus U3 squared. These are all real numbers, and they add up to 1. And this is a sphere. And so in particular, that means it must be 0 Maslov, and it's Lagrangian, I should say. Let's see. Lagrangian sphere, it's 0 Maslov and exact. It has to be because it has no first cohomology. It has to be 0 Maslov and exact. But there's a very famous theorem due to Gromov that says there do not exist compact exact Lagrangians embedded. Compact exact Lagrangians in Cn. So those don't exist. So that means this thing has to be a burst. So it says that what I've written there, it's a bit small. It says there do not exist compact embedded exact Lagrangians in Cn. And so that means that this Whitney sphere must be immersed, and indeed it's an exercise to show that L has a single transverse double point, self-intersection point, at 0. And I believe there were some talks about Willmore earlier in the week. So this thing is actually a Willmore surface. So it's a minimizer for the Willmore, or critical for Willmore in its homotopy class. It's the only genus 0 Willmore, Lagrangian Willmore surface, this thing. And actually, one way to think about it is it's like a compactification of the Lagrangian catenoid. That's one way to think of what this thing is. Any questions while I erase this board? Okay, so what my goal is to try to explain what this Whitney sphere wants to do. that's going to be one of my goals for this end of this talk, is to tell you what actually happens to this sphere. Right? This sphere cannot be a self-shrinker. That's impossible. So what does it do under the flow? Okay? That's what I'm going to aim at the end. But in the meantime, let me talk about some other special solutions that we can construct for the flow. So what have we got so far? We've got some special Lagrangians, we've got some shrinkers, we've got something that we don't know what it does, but there are some other special types of solutions to mean curvature flow that we can construct. And the next one is expanders. So what's an expander? So a Lagrangian L, or actually anything, L is a self-expander if and only if. So for the self-shrinker, we had that H was minus x perp over 2. For a self-expander, we have H is x perp over 2, so plus x perp over 2, which is the same as saying that the square root of t times L solves LMCF. T now positive. So it just expands and expands and expands. It exists for all positive times, but doesn't exist for negative time. Right? Now, luckily, my planes are still on the board. So I've got these planes, P1 and P2. Okay? They're defined by these n angles, theta 1 up to theta n. So let's let P1 and P2 be as before. The n planes in Cn as before. But now I don't have that the angles add up to pi, but I have them add up to something strictly less than pi. So rather than them equaling pi, I have them something strictly less than pi. Now, why is that at all interesting? Why is that an interesting statement? Well, this implies that the union P1, P2 cannot be volume minimizing. So now it explains, I'm explaining why Lawler cared about those Lawler necks, because this is Lawler's angle theorem. So what Lawler showed is that a union of planes is volume minimizing if and only if the sum of the angles is greater than or equal to pi. And the critical case is equals pi, and that's because of the existence of the Lawler necks. That's how the proof actually works. You show that that's the critical case, and then everything else you show is volume minimizing. But these ones cannot be because the Lawler necks beat them. Okay, so this thing cannot be a union of special Lagrangian cones, right? That's not possible. But I'm claiming there is something asymptotic to it that's interesting, and that's the self-expander. So this was proved by Joyce, Lee, and Sway, which said that there exist, it's going to look very similar to the statement I had about Lawler necks. There exist exact Lagrangian self-expanders L with the same topology asymptotic to P1 union P2. So you should think of it, I have a pair of planes that are like this, right? They're at right angles before. If I move them closer together, then I find an expander instead. So schematically, this is like the Lawler neck case, okay? You have like a hyperbola going between the two lines. And then if I have the angle smaller, then I have some kind of expanding curve that comes out looking like that. Right? That's what happens. Does that make sense? No, you cannot. No, you cannot. No, self-shrinkers, we don't have an analog for sort of non-compact self. You're thinking about non-compact self-shrinkers that are asymptotic to planes? That's what you're thinking? No, so when you make it greater than pi, there's nothing. Yeah, there's nothing, sadly. I see that sad look on your face. Maybe you should try anyway. I think you can get something singular maybe, but I don't think you can get something smooth. I mean, people have thought about it, but I don't know what happens actually. I was a bit hasty, but you don't get a self-shrinker, but I don't know what you get. Before Rob asked me, now the decay to these things is exponential. It decays exponentially. All right. And there was one more class of special solutions that I mentioned in my previous talk, right at the end, which was translators. So there's a very famous translating solution that one can write down, which is just a curve in the plane. So this has an overly dramatic name. This is called the Grim Reaper curve. So there are lots of ways to write this down, but I'm going to write it like this. I'm going to let L be minus log cos y plus iy, such that y is in minus pi by 2, pi by 2. Okay. So what does that look like? So I've got these two horizontal lines, pi by 2 and minus pi by 2. And then I have a curve that's asymptotic to one line at one end, comes around, and then it's asymptotic to the other line at the other end. Okay. So this is the Grim Reaper curve. And this is a translating solution to the curve shortening flow or Lagrangian mean curvature flow. They're the same thing in this case, and it just translates to the right. So this is a translator. This satisfies H is, I guess, 1, 0. Translates to the right. And I said that there was some function. Remember, I gave this lemma, right at the end. I said if you had a translator at 0 Maslov, then there had to be some coordinate that was in the span of 1 and theta, right? Well, in this case, the coordinate is y, right? That's my thing. So y and the Lagrangian angle are basically the same thing. Right? So the Lagrangian angle goes from minus pi over 2 to pi over 2. Right? So this implies that the supremum of the Lagrangian angle minus the infimum of the Lagrangian angle is exactly pi. Remember that I said almost calibrated was to say this was strictly less than pi. So that means that this thing is not almost calibrated. Therefore, L is not almost calibrated. But it is 0 Maslov. But is 0 Maslov. And of course, you can get translators then in all dimensions. Then this means if you do L times Rn minus 1, this is now a translator in Cn. Okay. But these are not almost calibrated, okay? So these ones, if we impose the almost calibrated condition, these could never show up as a singularity model. These could not show up as a type 2 blowup. It would be impossible because the almost calibrated condition is preserved. That couldn't happen. So it was thought for a long time that there were no Lagrangian translators that are almost calibrated, because this was the thing that you could think of So then maybe there isn't any others. And that was a reasonable guess, but it turned out to be wrong. And so here is the thing which actually turns out to be true. Remember these planes, because they're going to appear once again. So talking about translators, so let P1, P2 contained in Rn minus 1 be the planes n minus 1 planes as before. Oh, let me just make it n, it's fine. N planes as before, with, again, this condition that the sum of the angles is less than pi. That same condition, the sum of the angles is less than pi. Then the claim is, well, it's not a claim, it's a theorem. It's by Joyce, Lee, and Sway again.
So do you mean an R2n?
No, oh yeah, sorry. The n planes in R2n, yes, thank you. Thanks, Rob. I kept writing Cn before. Maybe I should write Cn, then I won't get confused. Yeah, thanks. Yeah, so now what I'm going to have is that they show that there exist exact Lagrangian translators L, which are topologically just Rn plus 1, which are almost calibrated. So that's the big sort of bad news, if you like, which are asymptotic in some sense to P1 union P2. Well, this doesn't make sense because this is of the wrong dimension. This doesn't make sense, but if I cross it with R, then it does, right? Okay. So now they're asymptotic to a pair of planes that meets along a line. That's what's happening. So before, we always had things that were asymptotic to two transverse planes. They only just met at the origin. Now, this is asymptotic to a pair of planes that meets along a line. Okay. And that line is exactly the direction of translation. And L translates along the R direction. And again, the Lagrangian angle is just whatever the final direction is. Right? There's a final direction in C. That will be the Lagrangian angle for this translator. Okay, so that's all of the stuff I wanted to say about the special solutions. Now I want to get to trying to understand what this Whitney sphere thing does. And to do that, I'm going to look at a whole class of Lagrangian mean curvature flows in C2, which are invariant under a circle action. Okay. So this is equivariant LMCF in C2. So what we do is we take a curve, or we take a curve mapping some interval into C and let L be gamma of S cos phi, gamma of S sine phi, such that S is in I and phi is in R. Okay. So this is Lagrangian. You can show that this thing is always Lagrangian. And because this has, and the circle symmetry is just rotation by phi. Okay? Just adding things to phi. Translation in phi, if you prefer. And circle symmetry, that'll be preserved by the flow. So that means that the Lagrangian mean curvature flow must become some flow of this curve gamma. That's what must happen. It has to be. So then we see, this is again a very simple exercise, that if I do dl by dt equals h, so this is Lagrangian, dl by dt equals h, if and only if d gamma by dt is equal to the curvature of the curve minus, you take the curve, you think of it as a point in C, you take its normal projection, and you divide by the square of the length of gamma. So this obviously goes bad at when gamma hits the origin. This goes strange when gamma hits the origin, but that makes sense because that's where the circle action degenerates. That's where that goes bad. Okay, so this is a nice fact. And then what's our Whitney sphere look like? Well, the Whitney sphere must correspond to some curve in the plane. There must be some curve in the plane that corresponds to the Whitney sphere. And what it is it looks like this. I mean, it's sort of obvious when I said that it was a sphere with a single double point. It must look like this. So where this is a right angle, and these are both, and this is also a right angle. So these are both pi by 4. It's a figure-8 curve, symmetric, and it looks like this. Right? All right, and now you can ask yourself, what does that curve do under this flow? What does it do? And the answer is the following. So let me write down what the answer is over here, and then I'll come back and draw a picture. So I have to tell you, what is the tangent flow? So Neves tells us that, well, it's compact, so it must have a finite time singularity. And the question is, what is the tangent flow and all that stuff? So this was proved. So I'm combining two different theorems. So this is work by Savas, Halilai, Smotzik. So this is one name. This is another name. Smotzik. And also work of Celso-Viana. And what it says is the following, that under Lagrangian mean curvature flow, the Whitney sphere, L, develops a finite time singularity at 0, where L shrinks to a point. Tangent flow is, so this is something that I skirted over in my presentation, is that I said it was a union of special Lagrangian cones. Some of those cones could be counted twice or 3 times or something. Right? They could be cones with multiplicity. I didn't say they all had to be different. It could be the same cone happening multiple times. And that's what happens here. You get the real plane counted twice. So you get this double density plane. And the type 2 blow-up, well, what should it be? Well, where's the highest curvature? So I'll draw it down here. So where's the highest curvature point on this Whitney sphere outside the origin? Well, it's going to be out here. That's going to be where the highest point of curvature is going to be at some point. And so it's going to look like it's going to become very, very thin and look something like this. Okay? That's what it's going to do. It's not going to self-similarly shrink. It's going to get thinner top, bottom, and then shoot in. And if you look here, that looks a little bit like the Grim Reaper curve that I drew over there. Right? So it's not completely unbelievable to say that that should be the type 2 blow-up. And indeed it is. So the type 2 blow-up is Grim Reaper times R. So that's what happens. So indeed, it's exactly as I said, what could happen is that even though this thing is zero Maslov and all that, and even though the tangent flow is special Lagrangian, multiplicity 2 though, you don't see a special Lagrangian as the model. You see a translator as the model. How the singularity is forming.
May I make a quick comment?
Yep. Go for it, Rob.
Yeah, thanks. Yeah, if these real slices or whatever these are called of the Whitney sphere, if in fact and I believe they do have maximum curvature at those extreme points.
Yep.
It's what's counterintuitive. This is what is that wouldn't those move in faster? That's why I'm surprised it's.
Yeah. So they do zoom in very fast, but yet somehow it's shrinking down here fast enough. Yeah, it is bizarre.
So am I missing something that this slice is not depicting? Is there something else?
Yeah, probably, yeah.
Okay, that's I just want to understand.
Yeah, no, you're right. Yeah, sure.
There must be more mean curvature in the other part we can't see, I guess.
That's right, because remember that the flow doesn't just see the curvature of the curve; it also sees this other term. Yeah, exactly. So there's curvature concentrated near the origin that you can't see in this picture. Okay, I want to talk about 2 more cases of the equivariant flow. I want to think about the next case, which is, let me do tori first. So what does this mean? If I want to look at an embedded torus, well, there are 2 cases. It can either enclose the origin or it doesn't enclose the origin, but let's take one that encloses the origin. Let's just take an ellipse with axes A and B. Okay. Now, if I take A equals B, I get a circle, and what should happen then is, of course, gamma perp is going to give me a term that's going to work with the curvature. This, of course, has to give me something that I know and love, and it has to be the Clifford torus. Okay. So if I take A equals B, that's just giving me the Clifford torus. That's all it is. I've written it in a different way, but that's what it is. Now, it was shown that if you take A much, much larger than B, so now you've got a very, very, very elongated ellipse, okay? Then it was shown by Grove, Schwartz, Smotzek, and Zamish, as well as Neves, that the flow develops finite time singularity at 0, but it does not shrink to a point. The tangent flow is P1 union P2 special Lagrangian, and the type 2 blow up. Is the Lagrangian catenoid. So the picture of what happens is that it exactly becomes something like the Whitney sphere. And you get a right angle there. Looking like that. Okay. So that's what you see. So it sort of collapses in faster this way than that way, and so it pinches and becomes like that. And so you could say, well, that's what happens if A is very large in comparison to B. What if A is actually very close to B? What happens? And so that was something that Evans, myself, and Felix Schulze looked at. And we showed that if A is about the same as B, doesn't matter how close, but A is not equal to B, then LMCF has finite time singularity at 0 and tangent flow is not the Clifford torus. So you see, if I take the Clifford torus and run the Lagrangian mean Curvature flow, then it has a finite time singularity at the origin. If I compute the tangent flow, it's just the Clifford torus again. Okay? That's what the tangent flow is. And what I'm saying is that if I perturb it, no matter how small an amount, then it will form a finite time singularity at the origin, but whatever it is, it can't be the Clifford torus. So that means it can't have all shrunk away to a point. That's not what happened. And the obvious guess is that it does this again. That's the guess, but nobody knows. Right? That's what you expect to happen, but you don't know. That's what happens.
One more. So these are perturbations in the class of S1 equivariant.
Yeah, this is always here. I'm just perturbing this ellipse. Yeah, this is always within S1 invariant. But in fact, our theorem is more general. It says that anything you do, it can't have a singularity that is still the Clifford torus if you do any of these perturbations that aren't in the direction of just scaling.
Got it.
Yeah, the theorem has nothing to do with equivariance, but I'm just keeping everything with the equivariant framework for simplicity. Yeah. Okay, now let me talk about cylinders. So let's talk about some non-compact equivariant Lagrangian mean Curvature flow. That'll probably be enough for today. All right, so then there's one more, which is cylinders. So what I mean is I take two planes, two lines meeting transversely, and I consider a curve asymptotic to those pair of lines. And there's an angle here, which I'll call alpha. Okay? Right, and what we've already seen is that if alpha equals pi by 2, then the standard hyperbola, well, I'll say it now, the standard hyperbola is exactly the same thing as the Lagrangian catenoid. If alpha is less than pi by 2, bigger than 0, then what we get is there exist the self-expanders. So I said that was due to Joyceley and Sway, but actually in this equivariant case, that was shown first by Anciot. So then the question is, what happens if alpha is bigger than pi by 2? So suppose now it lies between pi by 2 and pi. Okay? So you don't have a self-expander, you don't have a special Lagrangian. So what does the flow do? Where does it go? It has to go somewhere. It can't go to a self-expander, it can't go to a special Lagrangian. It can't do that. It has to go somewhere. And here, the answer is perhaps a little bit surprising. So this was shown, collection of work by Neves and Wood, which says the following. So then LMCF, in this case, has a finite time singularity at 0. The tangent flow is P1 union P2, special Lagrangian, and the type 2 blowup. So remember, this just means that the sum of the angles is pi, which in this case means that alpha is pi by 2. Type 2 blowup, well, once I've said that, then you know that it's going to be the Lagrangian catenoid again. So what happens is the following. So the asymptotically, the curve has to look roughly the same. It can't change, but then it has to go up and then dip down like that. Go up and then dip down like that. And it forms a right angle there. Up and then comes back. Goes up and then comes back. So that's what it does. Okay? It crashes into the origin, but as it does so, the angle has to turn in to become pi by 2. It has to do that because that's the special Lagrangian angle. It has to do that. So that's exactly what happens, is it becomes some curve looking like this. Okay, so that gives you a whole bunch of different examples which shows how the theory works in practice, and in cases where we can say explicitly what's happening for the Lagrangian mean curvature flow. So thank you very much for your attention.
Any questions?
Grayson's theorem, right? Yeah. So you don't. So no. So in fact, I mean, this already shows you something very different, right? We started off with something which is embedded and convex, and it's forming a singularity. So it's definitely not the case. And the same is true here, right? If we took these, it's going to be embedded convex, and they form singularities. So no. Not at all. It's not really clear. I mean, I should say that in the early work on Lagrangian mean curvature flow, there were sort of attempts to look at things like notions of convexity for Lagrangians and so on in terms of the Gauss map. And that does work okay, but it's very restrictive. So if you actually write down any of these examples, none of them satisfy those conditions. So it's a very strong condition to impose any kind of convexity property on a Lagrangian. So yeah, it doesn't seem like that's the right condition. It's sort of too Riemannian, like we shouldn't really be thinking that way. But it's absolutely a fair question, but it's definitely not what happens here. Yeah.
I have a question as well.
Oh yeah, sure. Yeah.
No, first go ahead.
Yes. Yes. Yeah, that's right. Well, exactly. So, I thought, okay, so on the one hand, it's sort of saying that it's not interesting because I can perturb it as small as I like and say that it doesn't happen as a singularity. So this fits in with this feeling that self-shrinkers are actually not generic singularities for the Lagrangian mean curvature flow. In fact, the generic singularity should be this sort of behavior where you see special Lagrangians pinching off. So in that sense, the Clifford torus is not very interesting in Euclidean space, okay? It's not interesting in Euclidean space. However, it's good that you asked me that question because I was going to point out something that in these talks I've been focusing on the Calabi-Yau case, right? I've been focusing on Cn in the Calabi-Yau case. In fact, it's true. So in that case, remember I said that the Ricci curvature of the metric had to be 0 and had to be a Kähler metric. Now, it turns out that the Lagrangian mean curvature flow is actually well defined whenever the ambient manifold is Kähler-Einstein. So it doesn't have to be Ricci 0, it can be Ricci as a multiple of the metric. So in particular, you could look at CPN and CP2, and CP2 has a Clifford torus in it, and then that is very interesting because now it's minimal. So now that is interesting. And so that was studied by my student Evans, this same one. So Evans studied the Clifford torus and its behavior under the Lagrangian mean curvature flow in CP2. And in CPN in general, that is interesting. But the one in Euclidean space, or the one in the real sphere, that one is not, does not appear to be interesting from that. Yep.
Can I ask one on there are other people in the room who have questions?
Yeah, I think there was a one before you, Rob.
Please go ahead.
I also have a question afterwards.
Go for it. You go ahead.
Is it my turn now?
It is.
Okay. So what I have a kind of vague question. So what do we have as control? Like supposing I want to go towards one special Lagrangian and not another.
Yep.
So I have choice of my initial surface.
Yep.
And what else do I have choice?
Yeah. So
to flow to yeah.
Yeah. So what you know, I mean, this is somehow the hard question in Lagrangian mean curvature flows. So there's lots of problems, but one thing you can say is that you don't just have the initial surface. You can ask whether your initial surface is Hamiltonian isotopic to that special Lagrangian. Right? Because I said that in the zero Maslov case, the Lagrangian mean curvature flow is a Hamiltonian isotopy, right? Because it's J grad theta, and theta is single valued.
Right.
So that's a purely symplectic topology question you can ask. So you can just say, is my initial Lagrangian Hamiltonian isotopic to that special Lagrangian? Now, we don't know the answer to that question, but suppose that it were true, suppose you knew it, then you would like to try to prove that it flows to that one special Lagrangian. Now, that turns out, as I will say on Monday, to be too naive. That doesn't quite work, but it does work in some situations. So that's basically the motivation for this thing called the Thomas-Yau conjecture. So the Thomas-Yau conjecture says, you can detect from your initial Lagrangian and from your initial Lagrangian angle whether you will converge to a special Lagrangian or not, a priori. That's the conjecture. Okay. So you should be able to tell just from the Lagrangian and its Lagrangian angle whether it converges to a special Lagrangian or not. But
a particular special Lagrangian or not.
Yeah, so and you can say whether it's a particular one by saying, does it lie in its Hamiltonian isotopy class? That would be the way to say. But as I said, the situation is more complicated, as you'll see, because there's a difference between Hamiltonian isotopy and homology and all these things, and you could have it that your thing is Hamiltonian isotopic to a Lagrangian, but then it decides to go somewhere else instead, because the class is telling it to go the wrong way. So then, but that's what you want it to do. Yeah, that's what you want.
Right. Okay. Thanks a ton. Okay.
I'll explain that on Monday. Rob, did you have a question?
If I may. Rukmini's question gave me a chance to think about mine. So that my question may be a little more muddled than I thought 3 minutes ago. But actually, I was thinking in R4 or C2 or locally there. But then you mentioned the Einstein case. In CP2, there's the real RP2.
Yes.
And of course, in S4 or R4, there's this Veronese minimal surface in S4, but I don't think it's Lagrangian. In CP2, it's Lagrangian, of course.
That's right.
Is there any, you know, the question is basically, I guess RP2 just sits still. Obviously, it's minimal. But is there any, I don't know if there's any interesting thing for actually, this is the naive part of it. I don't know if there are any special Lagrangian non-orientable things anyway in there.
Well, okay, so they're not special Lagrangian, but remember that we're in CPN, so there's no Lagrangian angle anyway. So we can't talk about special Lagrangian, we can just talk about minimal Lagrangian. And then you can have non-orientable because you can have RP2, as you said.
Sure.
But it's true that most people avoid the non-orientable case, but I think it's very interesting. And in fact, the RP2s play a crucial role in the work by Evans on the Clifford torus case. So he uses the RP2s as not barriers per se, but they're used to control what happens along the flow. So it's
said it was not naive question, a little bit murky, but thank you for
no, but that's I think it is super interesting. I mean, you could imagine something like you start with an orientable Lagrangian, right? Maybe it's S2, but then it somehow double covers this
exactly.
RP2.
That's what I was
Yeah. This you can show that this happens, I think, in CP3. I don't know about CP2, but in CP3 that's been shown that happens. You can have Lagrangians converging with multiplicity 2 to the RP3. So I assume that it happens in all the CPNs. But
okay, thanks. Nice talk also, as usual.
Thanks, Rob. I think there's another question up there. Oh, yeah.
So when A is close enough to B, you mentioned that we don't know the blow up.
No.
What is the difficulty in figuring it out?
Yeah, so actually it's a bit like, who was talking about Wilmore conjecture? Somebody was. It was you, right? You mentioned the Wilmore conjecture. Someone did anyway. Someone mentioned the Wilmore conjecture a minute ago. It's a bit like that. You want to say, so you know, whatever it is, it has to have entropy less than the Clifford torus. It has to have less entropy. So the difficulty is to say, can we classify all of the Lagrangian, solitons that have entropy less than the Clifford torus? Like, can we say that, once you're below this, then you have to be one of these three options or something? Some kind of classification thing based on like area, or this is the weighted area, the entropy. You want to have something like that, and that seems very hard. You just don't know. So we can guess that it might be this two planes because that's there. So the two planes is a possibility. There's the cylinder that's a possibility, but that's it, right? So you don't have many options for what it could be that we know of. But there could be some magic other one that we have not seen. You'd like to prove that that does not exist. You want to prove there's somehow some gap in the entropy that says as soon as you go below the Clifford torus, the next one is the two planes. That's what you want to say. So that has entropy strictly bigger than 2, and this one has entropy exactly 2, and so you want to say there's nothing between 2 and whatever that number is. That it is for the Clifford torus. I mean, I calculated it at some point. I can't remember what it is. It's some very explicit number to do with pi. Forget. It's a bit like that.
All right, if there are no more questions, let's thank Jason again, and also the organizers and the staff for organizing this great week of talks.